Hello there. In this video we're going to continue our discussion of the power series of particular functions. So what we're going to begin by doing is supposing that f of x is equal to the sum from k is equal to 0 to infinity of ak times x minus a to the power k. So we have that this expression is the power series of f, or the power series representation of the function f. So pretty much as we use this expression, you will see that if you have some function in space, and you have this power function centered around, say, x is equal to a, regardless of the number of terms you include in this expression, it's possible that this power series breaks off, or something like that. Maybe not too close to the number a, but maybe like there. So this region here, so if this distance is r and this distance is r, then we say that there's a radius of convergence for this series, and this area is called the interval of convergence. So in this video we'll discuss how to figure out what the radius of convergence is for a power series so that we can know when to trust a power series and when not to. To begin our formal discussion of the radius of convergence for power series, let us first consider the Taylor series for a function for which we already know the Taylor series of, namely the natural log of the function 1 plus x. So it looks like that. So we know the Taylor series for this logarithmic function, t of x, is equal to the sum from k is equal to 1 to infinity. And I'm going to make the infinity an arbitrarily large number. We'll start at 2. Negative 1 to the power k plus 1 times x to the k divided by k. So this is the Taylor series for my function natural log of 1 plus x. So we can see if the x values are really close to 0, then the Taylor approximation is relatively good. At least for n is equal to 2, we can go up to 0.3 and maybe get a decent approximation, but that's subjective. So let's increase n to 10. So if we increase n to 10, that is, include more terms into our Taylor series, notice that the accuracy gets a little bit more better, but of course within like, a hundredth of a difference. 0.8 may be bad or good depending on how accurate you want it. So if we increase the number of terms to 100, then we can go up to this point here. It's like 0.98, and the accuracy is pretty good. It's within 2/100ths of a difference. So we can go up to 1,000, and the accuracy should be even more better. So notice it goes up a little bit more. Assuming it's not lagging. It is. So maybe too big. Or we broke it. There we go. It took a couple moments. So we see that as n gets close to infinity, the function is pretty good up until this point of 1. And if we pretty much zoom out and assume that this compiles in time, then you can see that pretty much this function is good up until the point as x is equal to 1, and you'll be able to see that as x gets close to -1, once it compiles, then our function pretty much approximates the curve relatively well. So we see that on the interval -1 to 1, we're open interval at -1 because it's discontinuous there, and up to 1 because it doesn't seem to be getting any closer to f as x gets past 1. This is what we call the interval of convergence. And since we're centered at 0, we call the interval 0 minus 1 and 0 plus 1 the interval of convergence. So that's just an observation of the natural log Taylor series. So let's look at another one. So let's look at another Taylor series that we do know, for example, e to the x. And its Taylor series t of x is equal to the sum from k is equal to 0 to infinity. I don't want to go too big. I don't want to break the system. So this is my Taylor series. Now to sort of see the difference here, I'm going to make the upper limit a little bit smaller, say n is equal to 2. So when n is equal to 2, notice that the function and the Taylor series definitely do have some discrepancy. And if we go to infinity, we might not be able to see much of a difference here unless we really go outwards. The primary difference is definitely on the left-hand side, but definitely there is some discrepancy between the Taylor series and the function on the right-hand side. So if the left-hand side is the issue here, so I'm going to increase n. So where is this almost approximate, like x equals negative 2.7? No, a little bit more. It's 3.2, 3.3. Somewhere around there, you may subjectively think that it's a good approximation. So if we increase this value n, our goal is to have this a little bit more accurate. So let's increase it to 100. So once it compiles for 100, it definitely is more accurate on that interval. And we can sort of zoom out and see where it goes. And we see that it's definitely a lot more accurate on a larger interval. So notice we have the blue curve here, and there's definitely not that much of a difference, unless you really zoom in. But of course, since this is a 100th degree polynomial, it is even, so it definitely will go to positive infinity on the left eventually. But nonetheless, we can see as we make n larger, the Taylor series approximates the function on both the left and the right. So we say that the interval of convergence is the real line and the radius of convergence is infinity. So that's more of a graphical understanding of the radius of convergence. So now let us look at algebraically how to find what the radius and interval of convergence are. So in general, if TF is centered around or centered about x equals a with ratio or radius of convergence r, then the interval of convergence is going to be equal to a minus r and a plus r. Now whether you are to include these boundaries or not in the interval of convergence, we'll discuss that in the next video when we look into some of the details. So a rule to find this value r, which I'm not going to prove, but using the ratio test, one can find that r is equal to the limit as n goes to infinity of a n divided by a n plus 1, its absolute value. So let's demonstrate this relationship with an example. So example 1. Suppose we have e to the x is equal to the sum from k is equal to 0 to infinity of 1 over k factorial times x to the k. So here, these are my constants for my Taylor series, and this expression tells me where it's centered around. It's centered around 0, the origin, so we don't really need to consider what a is. So a is equal to 0, and our goal is to figure out, okay, what is r equal to so that we can find out what the radius of convergence is. So just from this setup, we know the interval of convergence is going to have the framework minus r, or 0 minus r, and 0 plus r, where 0 is coming from where this Taylor series is centered around. So r is going to be the limit as n goes to infinity of a n divided by a n plus 1. So a n in this case is 1 divided by n factorial. N plus 1 is 1 over n plus 1 factorial. So when you reciprocate both of these, you're going to get the limit as n goes to infinity of n plus 1 factorial all over n factorial, which can expand downwards. So n plus 1 factorial is just the same thing as n plus 1 times n factorial all over n factorial. Your factorial expressions cancel, and we have that this is equal to the limit as n goes to infinity of n plus 1, which we know is equal to positive infinity. So this is what R is. So the radius of convergence is infinity, which we sort of saw in the graphical demonstration. Therefore, the integral of convergence is minus infinity to infinity, which is the entire real line. So as our second example, let us take a look at the series. The natural log of 1 plus x is equal to the sum from k is equal to 1 to infinity of negative 1 to the k plus 1, x to the k, all over k factorial. So before, graphically, we saw that the radius of convergence was equal to 1. So we see that this is my constant, ak, and this expression is the same thing as writing x minus 0, the quantity squared. So a is equal to 0, and our goal is to find what r is equal to find the radius of convergence, to find the interval of convergence. So r is going to be equal to the limit as n goes to infinity of an divided by an plus 1, the absolute value. So this is going to be equal to the limit as n goes to infinity of an, so that's going to be negative 1 to the n plus 1 all over n factorial, times the reciprocal of the other part, which is going to be equal to n plus 1 factorial divided by negative 1 to the n plus 1 plus 1. So the absolute value of negative 1 to any power is going to be 1. So this is just going to be equal to the limit as n goes to infinity of n plus 1 times what? So this should not be n factorial, this should just be n. So this should just be n. Okay, great. So as n goes to infinity, what does this ratio go to? So this goes to at least infinity over infinity if we just look at the piece by piece terms. So we can use L'Hopital's rule to quickly verify this, or you can use your rational limit theorem. But in either case, this is going to be equal to the limit as n goes to infinity of the derivative with respect to n of n plus 1 over the derivative with respect to n of n, which is equal to the limit as n approaches infinity of 1 divided by 1, which is going to be equal to 1. So this is the radius of convergence. Our center of our interval will be 0. So that means the interval of convergence for the natural log of 1 plus x series that we stated is going to be equal to minus 1 to 1. Now, if you want to test the convergence of the endpoints, you simply just plug these numbers into the original series and determine whether that series converges or not. And in the next video, we'll work through a couple examples where we actually do that.